Problem 2 gives us two balls of different masses that are starting at the same height, and they're asking us two-part problem. One, which sphere hits the ground first, and two, which sphere bounces highest. And it asks us why for both of these. So the math will answer the why part of these, and we're just going to take this problem in 2 steps. So first, we're going to make assumptions like always. The first assumption I made is that the starting velocity and time for both of these balls is going to be 0. That means they're both starting completely at rest and in the same instant. And then 2, I'm assuming elastic collisions. Which means none of the energy is going to be transferred into the ground. In real life, there'd be some heat generated, some sound generated, maybe it was a sticky surface, and something happened where energy from the fall is transferred into the ground, and that's why realistically when you drop a bouncy ball, it doesn't reach your hand. But we're going to make the assumption that is perfectly elastic collision where all of the energy is staying in the system itself. Okay. So for problem 1, we want to figure out which ball hits the ground first. So we're going to do an conservation of energy equation. We're going to use this a lot in all of these kind of problems, so this is one that you should memorize. U initial plus K initial equals U final plus K final plus W. So U is our potential energy. Usually in most problems, it's going to be mass times acceleration due to gravity times height, because potential energy due to height is a very common thing that we experience. There are other forms of potential energy, specifically springs, that we will see, and you'll need to know those equations as well. K is our kinetic energy equation, 1/2 mv squared. And then the last component of this is W. That's work done. So sometimes a system will do work out, which is essentially energy being applied outside of the system. This is going to be 0 because we're assuming an elastic collision. If, for example, these balls hit the surface and the surface was pushed, that would have been work out of the system, and therefore some energy lost out of the system. So we have mgh initial plus 1/2 mv initial squared equals mgh final plus 1/2 mv final squared. So we know that this second component, it goes to 0 because the initial velocity of either ball is going to be 0. And then we're going to let this third component, go to 0 as well, because our final height is going to be 0 the instant as these balls hit the ground. So that leaves us with mass times acceleration due to gravity times our initial height equals 1/2 mv final squared. And if you can see here, mass is going to cancel out. And if you want to solve for your final velocity, it's just going to equal gravity times your starting height times 2, the square root of 2 times gravity times height. And this is your final velocity at any height for any ball with any mass. And that's why I didn't even specify when we started this equation whether I was looking at ball 1 or ball 2, because the mass is independent of the final speed. And this is, for example, why, like on the moon, when you drop the bowling ball and the feather at the same time, they hit the ground at about the same time, because they generate speed specifically based on the acceleration due to gravity, and their final velocity is mostly dependent on just that and how high they started. The mass does not play a component in that when we are assuming things like no air resistance, perfect elasticity on collision. Part B asks us which one's going to bounce higher. So some of you might think that because even if they have the same speed, one has more mass, so it'll be harder to go back up. We're about to find that out, but spoiler, they're going to have the same height as well. So we're going to go back to our initial equation. And again, there's no work being done outside of the system. And from there, we can go and draw our usual equation. Okay, and now our assumptions that we're going to make. We're going to call the initial point, the moment that the ball leaves the ground after it starts to bounce. And at that moment, when it's officially stopped moving downward and has started to move upwards, it has an initial velocity of 0 again. And then at its peak is exactly where it stops moving upward, therefore it has a final velocity of also 0. So we just get left with these two components, and mg h initial equals mg h final. You can see where this is going. M and g just cancel out, and you get left with your initial height is always going to equal to your final height. So the idea here is with no energy loss from the system, assuming it's an elastic collision and there's no air resistance, the ball's not going to make any sound or heat when it hits. And because there's no energy loss, the masses are irrelevant to the speed the ball's going or the height the balls are going to bounce afterwards. Problem 3 asks us to find how high on the ramp this ball will travel once it's released. And then it asks us to also solve it if we included friction in that problem. So that comes to our first assumption, that there is no friction along this ramp. So from here, this is just a simple conservation of energy problem. U initial plus K initial equals U final plus K final plus work. In our first run at this problem, we're assuming that there is no work done, because that's where friction would go later, and no other energy is being lost from the system. We're going to go ahead and assume that our initial velocity is equal to 0. So we have no initial kinetic energy. And then our final velocity is also going to be 0, because the highest point that the ball will go on the ramp is right when it stops and starts to come back down. So we just have mass times acceleration due to gravity times our initial height equals mass times acceleration due to gravity times height final. And we get the same answer that we did with one of our previous problems, where our final height equals our initial height. And this makes sense again, because the only energy inputted is potential energy, and there is no energy loss, so your end potential energy has to be the same exact height. If we go ahead and include friction in this, things change only ever so slightly. We get the same equation, ui plus ki plus u equals uf plus kf plus work. In this situation, only our kinetic energies go to 0, and you get left some work due to friction. So you get mgh initial equals mgh final plus some work done. So now we want to solve for height, solve for our final height. So we have h final is going to equal mghi minus work divided by mg. And you're going to get your final height is equal to your initial height minus your work done over mass times the acceleration due to gravity, which makes sense that your final height is less than your initial height because some energy is lost due to gravity. Due to friction, excuse me. Problem 4 is another conservation of energy problem. You have a ball at some height at the top of a ramp, and the question asks us how much this spring is going to compress. So this is a very similar problem, except the only difference is that the second potential energy is not going to be due to height. It's going to be due to the compression of the spring. So our assumptions, we're going to assume no friction, and we're going to assume our initial velocity equals 0. So if we set up our conservation of energy equation, it's going to be the exact same as usual. I know it might seem redundant to write out the whole equation if we know there's no work done and we know initial kinetic energy is going to be 0, but it's still better to write it all out so you can explain to your interviewer that you understand why you're making these shortcuts. And it also takes a little bit of time, maybe saving you from an additional question. So kinetic final is also going to go to 0 because the maximum compression is going to be when that ball finally stops moving in the rightmost direction, starts moving back towards the left. So we just get left with these two potential energies. The first potential energy is completely due to height, So we have an initial height, but U final is solely due to the compression of the spring. So potential energy due to a spring is 1/2 K being our spring constant and times x squared, x being the compression or displacement from equilibrium in the spring. And in this situation, we want to solve for x. X equals 2 times mgh, all divided by k to the 1/2. And that's our final answer.